Okay, for the next part of our journey, we're going to show how to create the part using additive manufacturing. So we identified the part in the assembly that we're going to change. Now this is going to be a totally new part. It's going to go from 6 pieces to 1 piece. We're going to change the airflow because potentially, with 3D printing, we can curve things and make things that you couldn't make with conventional tooling. And then we will end up doing some analysis to make sure it's a good part, and we will put it in the print tray. So what we have here is a new part. I just called it 6-to-1 top out for topology optimization. And we really don't build parts, we build assemblies, we build components, we build machines. So we work in context of the assembly, we always have, and we always will. So with NX being a complete end-to-end solution, these tools are just like tools that you've always used, but now they add some additive manufacturing capabilities. So if we go into assemblies, and we can use associativity, we'll make this our work part, and we're going to associate the old part to the new part so that we can capture what we need from the old part and bring it into the new part and redesign the part. So what we'll do is we'll use our wave geometry linker, and we're going to bring in the information that we need. So we're going to need that part, and we'll hit apply, and we're going to need this part, and we'll hit apply, and there's a part here, apply. We're going to make all of these into one part, and then this part, and this part, and I did them one at a time just to show that there are 6 parts. So now that we have the 6 parts and they're associative in our other model, we'll just open up our other part. So now we're in the 6-to-1 part, and you can see that the 6 parts have been wavelinked into this part so that we can use the information that we need to build this with additive manufacturing. Okay, so let's take a closer look at these parts individually and show how, now that we have them, we can use the information from the parts that we need, but the parts of it that we don't need, we won't use. So if I bring on the first part, this is definitely one of the parts that we're going to redesign, and we're going to build some information off of it, like kind of like tooling information, because the way additive thinks is you put in the information and then it gives you the part with the information that you put into it. So the next part is this part, so that's linked in there, and we're going to need this outside surface, and the next part is this part, so we're going to take that and combine that into the other 2 parts there, and then of course these here we'll just put on individually. But now that we have all of them, what we're going to do is we're going to start modifying them. And with this, I was able to take this part and just using delete face, I was able to delete everything except for the inside chamber, because that's what I wanted. So I deleted everything but the inside airflow. And then we were able to do the same with the other part so that we could combine the 2 parts together, and then we could kind of like start making design changes using synchronous technology to get the information that we need. So if we kind of walk through our design, you'll kind of see how we've got this information. So now we united those parts together, and if we we're kind of rebuilding the design, but you see how we're able to create a bridged piece of airflow. Now with conventional tooling, you may not be able to do that, but with 3D printing we can do that. We can now curve the design and get a new design. So we developed basically the airflow of our part. Now we have the outside shape that we want to use. So we've made some modifications to the outside shape that we have, and filled the inside. So what we're doing is we're developing a design space. This is the space that the design must stay within, and then we develop the airflow. So this is what we're going to put into our optimization. And now a very important part, this here, that is the outside shape, because the part still needs to fit in. So we're going to tell it that you have to stay within this design space. This is the airflow that we need, and you have to match the old part in this area. And by doing all of that, we're able to run the topology optimization, and we'll do that next. And we're able to come up with many, many different design scenarios. So for instance, here's one design scenario. Notice it has the airflow that we want. It matches the outside shape so it'll still fit in the part. And this is one of our optimizations. Possibly this open profile wouldn't be a good idea, but we could, once we have it once, we could run it many, many times. So possibly this could be our output. Now this doesn't have the open inside like the other one. It is pretty beefy though. Possibly we could reduce mass. We really don't care about weight for this, but in many additive manufacturing scenarios, weight is super important. So we could run it again, and we could get many, many different scenarios. So this one's more lean. This is actually pretty nice. This, to me, is what we're looking for. And because we're printing it in plastic, we don't have to worry about supports with, with the multi-jet fusion, because it prints it in the powder that it actually makes the part in, so it builds its own supports. And you could nest many of them at the same time. And just show you a couple more examples. So here's another example. But what's nice about this is you can make many, many different examples. And then you can go to a design review, and you could have your engineers and your peers, and you could look at the different designs, and you could, try to figure out up front which one we're going to go with. Now, I can't tell you how many times I've been on projects and we would start with one design, and then we would, it would be too far along in the design cycle, and we wish we had taken a different route. Well, this tool allows you to come up with many upfront scenarios, different design characteristics, different materials, and then you could decide we're going to go this route. So it's very, very helpful in that sense. This one here, you could control the spread of the material because we're printing it in powder. We don't have to worry about supports. We can get away with a skeletal structure that looks like this. And to make it even more powerful, then we could start using convergent modeling. So we could start doing things like we united these on, and we could start offsetting these shapes, add additional features for improving the model, and we can unite things together. So basically we could do what we've been doing for generations in CAD with traditional modeling, and take faceted data, whether it's made with topology optimization or a scanner, and we can merge these worlds together, and we could come up with different design scenarios that work together. So now what I'm doing is I'm uniting all these parts together because we decided this is the one we're going to go with, and here it is. So we're happy if I hide everything. you can see the finished part. And there it is, using topology optimization to make the part. 6 parts all built into one part. Because it's plastic, we don't have to worry about supports. If it was metal, we'd have remedies for that too, where we know that we're going to use supports. Very important. We're able to change the design of the airflow, improve on that. We don't have to worry about the cost of tooling, and we can make as many of these as we want at any time that we want. And then if we go back to our top level in the design, and we turn off the old design and turn on the new design, there it is. So done in context of the assembly using additive manufacturing. So as a designer, this tool is made for a designer. I can come in, I can use the additive manufacturing tools in context of the design and do my job like I always have and do it even better.